Hello viewers. In this presentation, we are going to talk about fundamentals of thermodynamics and first law of thermodynamics. The study of heat and its transformation to mechanical energy is called thermodynamics. It involves the description of matter in terms of macroscopic properties such as pressure, temperature, volume, and heat flow. Thermodynamic system is an assembly of an extremely large number of particles having a certain value of pressure, volume, and temperature. A collection of molecules in a gas-filled container can be considered as an example of a thermodynamic system. Thermodynamic systems can be classified into three categories: isolated, closed, open. In isolated system, neither energy nor particle can enter or leave the system. In case of closed system, energy exchange is allowed in between the system and surrounding. In open system, both energy and particle exchange is allowed in between system and surrounding. At equilibrium, the definite values of pressure, volume, and temperature of a system at any time represent the thermodynamic state of the gas. The variables which determine the thermodynamic behavior of a system are called state variables. The general relationship between pressure, volume, and temperature for a given mass of the system is called equation of the state. The continuous change in the state of a given sample of a gas is called a thermodynamic process. If the temperature of a system does not change during a process, the process is called isothermal. Its representation in PV diagram is as follows. If the pressure does not change during a process, the process is called isobaric. Its representation in PV diagram is as follows. If the volume remains constant during a process, the process is called isochoric process. Its representation in PV diagram is shown here. If no heat enters or leaves the system during the process is called adiabatic. The representation of an adiabatic process is as follows. The laws of thermodynamics are elegant and compact generalization of experience. They are treated in a wholly macroscopic way. Zeroth Law of Thermodynamics states that two bodies or systems that are in thermal equilibrium with a third body are in thermal equilibrium with each other. In the following illustration, both A and C are in thermal equilibrium with B, which means A and C must be in thermal equilibrium with each other. Consider a gas container fitted with a movable piston is at position A corresponds to pressure P1 and volume V1. Let the gas expand very slowly and attain the state B corresponding to pressure P2 and volume V2. Both the states are in equilibrium. We are asked to find out the work done by the gas during this expansion. Let's evaluate the expression for work done analytically first. If capital A be the area of the piston, then the force exerted by the gas on the piston is F equal to PA. Now, if we consider the gas expands and moves the piston outward through a small distance dx, then the small amount of work done dW by the gas on the piston is going to be dW equal to F dot dx, or in other words PA dx, which can be written as P dV. To get the entire work done, we have to integrate dW from initial volume V1 to final volume V2, which will lead to us W equal to integration V1 to V2 P dV. We can also evaluate the expression for work done from PV diagram. Suppose the gas undergoes a small expansion delta V at pressure P. Then work done by gas in such an expansion is delta W equal to P delta V. Therefore, the whole work done is nothing but the summation of the small work dones, which will lead us W equal to sum over P delta V. The expansion delta V is positive, so that the work done by the gas is positive and area under the curve in PV diagram is also positive. If area under the PV diagram is traced in the clockwise direction, the work done by the gas will be positive, and if the area is traced in the anti-clockwise direction, then the work done by the gas will be negative. The work done in taking a gas from one state to another depends not only on the initial and final states, but also depends upon the types of processes. Whenever the volume of a gas changes, the work done by or on the gas changes regardless the process involved. A thermodynamic process may be a non-cyclic and cyclic. A non-cyclic process is one in which the system does not return to its initial state. That is, the final state of the system is different from the initial state. A cyclic process is one in which the system returns to its initial state. A non-cyclic and cyclic process in PV diagram is shown here. Now let's evaluate the work done in a cyclic process. Work done is equal to the area enclosed by the closed loop in the PV diagram. Now let's discuss first law of thermodynamics. According to kinetic theory of gases, the molecules of an ideal gas do not exert intermolecular forces. Therefore, the molecules of an ideal gas do not possess potential energy. As a result, the internal energy of an ideal gas is wholly kinetic in nature and is a function of temperature only. In practice, however, no gas is ideal. The molecules of a real gas exert forces of attraction on each other, so they also possess potential energy. This sum of kinetic energy and potential energy of the molecules of a gas is called its internal energy. The first law of thermodynamics is based on the idea of conservation of energy principle. The heat energy added to a system can cause two changes. It can rise the temperature of the gas and thus increase its internal energy, and it can cause the gas to expand, allowing the gas to do work. This is the foundation of first law of thermodynamics. The heat energy supplied to a system is equal to the increase in the internal energy of the system plus the work done by the system. Mathematically, it can be expressed as Q equal to delta U plus W. Now let's evaluate the work done during an isothermal process. For isothermal process to take place, the cylinder should have conducting walls. The gas should be compressed or allowed to expand slowly. The expression for work done in isothermal process is W iso is equal to nRT ln V2 by V1. For adiabatic process to take place, the cylinder should have insulating walls. The gas should be compressed or allowed to expand very quickly. The expression for work done in an adiabatic process is W adiabatic is equal to R times T1 minus T2 by gamma minus 1. Any process which can be made to proceed in the reverse direction so that it passes through exactly the same states in all respects as in the direct process is called a reversible process. The PV diagram for a reversible process is shown here. A process can be reversible if it takes place at extremely slow pace and free from any sort of energy loss. As we can understand, first law of thermodynamics is a form of principle of conservation of energy. The first law of thermodynamics failed to answer the following. It does not indicate the direction of heat transfer. It does not tell anything about the conditions under which heat can be converted into work. It also doesn't tell why the whole of heat energy cannot be converted into mechanical work continuously. To summarize, here we have discussed fundamentals of thermodynamics, zeroth law of thermodynamics, and first law of thermodynamics.